All right. Ladies and gentlemen, recording has started. For regular listeners to the Honors Physical Science podcast, Nick is not here today. I believe he's on a field trip, so your normal greeting won't be there. But feel free, try somehow to carry on. All right. Plan for today. First question, is the test still Monday? Yes, the test is still going to be Monday. We have a small amount of information that we have left to cover. It's my sincere belief that we can get it done in a reasonable amount of time. Under the following conditions. So, I don't usually do this, but today I'm going to, because of the fact that we really need to get to the material. I'm going to talk, you're going to listen. Okay? If you have a question, write it down like in the margin or something like that, and we can come back at the end and we can deal with questions at the end. But I really need to get through this material first, then we can talk about it. Okay? It's fine.
I'm pretty sure.
If you listen to the podcast, you'll find out. As far as the packet goes, we've not done the first 3 pages of the packet. We are not going to do the first 3 pages of the packet. You are not going to be responsible for the first 3 pages of the packet, except for the HR diagram, which we could use in the life cycle of the star. There's a big version of the HR diagram that's on page 3, but there's also smaller versions later on. So, anyway. What I will do is right after when your class is done, I will go to the library and I will look at the objective sheet and I will cross off anything that you're not responsible for on the objective sheet. Okay. So if you've already printed out a copy of the objective sheet, you might have to go back real quick and look and see if I got it.
If you have extra time, which you probably won't, you should make an objective sheet for the final.
You think?
Yeah.
Well, wouldn't it just be all of the objective sheets?
No, because that's how it happens.
Yeah. All right. With that being said, let's move on. Okay. Yesterday, at the end of class, after we finished up life cycle of stars and where ultimately, these stars end up, we shift our focus to the last part of this section, and that deals with a question. How did it all begin? It's a logical question that comes up. How did the universe start? How did we get here? Where did it all begin? That kind of stuff. So as scientists, first thing that we do is we gather evidence. We make observations, and then we try to make a pattern out of those observations. So the first observation that we talked about was stemming from the Doppler effect. Right? The Doppler effect is the change in the perceived frequency and wavelength of a wave due to the motion of either you as the listener or that object as the source of those waves. We talked about in class yesterday that most of your experience with the Doppler effect probably is limited to sound. That if you something that is moving, that is making a sound. The best example I can think of is if you watch a car race on TV, and if you watch the cars go past, they make a different sound when they're coming towards you than they do as they're going away from you. Because of the motion of that object, it changes the wavelength and the frequency. Our ears pick up frequency as a change in pitch. Okay? But in observation of light that is coming from distant galaxies, we see that light undergoes a Doppler effect, either towards the red side, meaning that those objects are moving away from us, or towards the blue side, makes the object move towards us. So we take these observations, and then Hubble, back in the 20s, putting them together, right? Hubble's law. Remember, a law just tells us what is happening. So what Hubble says is that based on this evidence of the red shift coming from most light of the galaxies that we know about, he puts together and says, well, that must mean that those galaxies are moving away from us. And if the galaxies are moving away from us, that must mean that the universe is expanding, that it is getting bigger. Okay? And that Galaxies that are farther away from us, then we see that are actually moving faster than the galaxies that are closer to us. So the farther away they are, the more that they're expanding. That's Hubble's law. It tells what is happening. Evidence that the universe is expanding, which I think is the last thing on the front page. Is that correct? No.
The last one is like these galaxies are moving away from.
Oh, so galaxies that are farther away from Earth are moving away from us faster than galaxies that are closer to us. All of that put together tells us that the universe must be expanding.
So these galaxies are moving away from Earth.
All right, ready there? So now we have a law. Law tells us what. The next step is to develop a what? A theory that tells us why. And that theory we refer to, well, first, we got to do some math. Okay. If these galaxies are moving away from us, it would suggest that they came from a previous spot, based on what we know about motion. So you work backwards. You know how fast these galaxies are moving based on their redshift. We kind of know how far away they are. So we know how fast, we know how far, we can work backwards and find time. And we find out that if everything moves the way we think it should, that approximately 14 to 15 billion years ago, all of that stuff was in the same spot. So we come up with the Big Bang theory to explain why all of these things are happening. The theory says that the universe, as we know it, came into existence in a single moment during an event known as the Big Bang. That at one point, back approximately 15 billion years ago, all of the matter and energy in the universe was concentrated in a single point. Now, was it as big as the period at the end of this sentence? I don't know, maybe. Alright? But everything that we know that exists in the universe, stars, planets, meteors, all that other stuff, at one point existed all together. Now, so, quick, Sam, I know what question you want to ask, so ask it.
Like, what was it just like a blob? Like,
Yep.
what else was around it? Just
Nothing.
So it was like a little blob on like a whiteboard. Everything else
Except the
was
whiteboard's not there.
So what is
But
it?
then where, like,
Nothing.
but that just
So
like,
what do you mean? Like what color is it?
Nothing.
It was just one dot.
Yeah.
Oh, are you serious?
yeah, but like,
Oh my god.
it can't just be like
Space
So
was
weird.
Warned ya. I warned you on the opening screen today.
Who's that?
Wait,
So
what is
that,
nothing?
so that's the,
What?
so here's the thing, okay? If the universe is expanding, you can think of it like a balloon, okay? However, you can't think of it as a balloon that I'm blowing up like in this room. Because if I blow the balloon up in this room, eventually what's going to happen? Well, yes, an indestructible balloon, right? Eventually, what's going to happen to the balloon? It'll get as big as the room, and it stops. And it'll take the shape of the room. That's not what the universe is like. There is nothing outside of the balloon. What do you mean nothing? Nothing. It doesn't exist outside of the balloon.
I know, I can't even think of it.
Good.
How can it expand into nothing?
Good question. Don't know. That's
Nothing.
kind of the thing. How can it expand into nothing? It's like rewriting the rules. Like nothing exists. Oh, now it does because I just moved there. Nope, now it does because I just moved there. So, yeah. So,
But where did that speck come from?
Wait,
good question. We'll get to that a little bit later.
didn't come from anything.
Yeah, like what is nothing?
What was before the step? Was anything?
We'll get to that in a little bit. Hold on. That'll sufficiently blow your mind even more. So.
Nothing.
All right. So
God in
Pretty
that little
close, I don't
speck.
let's talk about a couple of things. Okay, let's talk about a couple of those things. First, if all of the matter and all of the energy in the universe are concentrated in a single point, is it as big as this period? I don't know. But remember we talked about during nuclear reactions, what happens to some of the mass in that nuclear reaction? It gets lost and it gets turned into what here? Energy, right? That whole mass energy equivalence idea. If all of the matter and all of the energy in the universe is condensed in a single point, do you think a lot of it is in the form of mass at that point in time? Because mass can't be in the same place at the same time. Energy can't, though. You have as much energy as you want in a little single point. Well, but if all of the energy in the universe is condensed into a single point, how hot do you think it is? Pretty hot, right? And pretty unstable. So what happens? Boom. Big explosion. Okay? Say again?
Why did it stay a point and then happen?
Hold on to that. It might not have stayed a point here, but we'll talk about that in just a second. So, after the Big Bang Theory, or after the Big Bang of the Big Bang Theory. Come on. So, everything was really hot at that instant before the explosion and directly after the explosion. But after the energy starts spreading out, now the universe begins to expand. And as it expands, it cools down. And as it cools down, some of that energy now turns into matter. And then that matter begins to cool down and form into things like nuclei, protons, electrons. And then it cools down a little more, and then it starts forming atoms. Because if everything is so hot, will atoms form? Will anything structured form? Because if it's so hot, what happens when things get hot? They do what? They move, right? And if they move a lot, are they going to stay together in a form of an atom? They're not. So right after the Big Bang, there really isn't atoms. There's just a bunch of energy. But then those energy begins to cool. And through mass energy equivalence, it turns into matter. But then even after a while, it's still too hot to form a nucleus, atom. But after a while, it does. And then eventually, after those atoms start forming, right, gravity starts taking over, starts pulling those things into, nebulae and stars, and then it all kicks up as we know it.
Oh wait, where did it come from, that little dot?
Come on.
Keep waiting.
I know. I have to though. So, because there's a lot. It comes up. It's a logical question.
It's like, there's a sonic explosion. It falls down.
So, after a while, it tends to cool. It cools down a little more. Blah blah blah. We form stars. We form planets. We form all that good stuff. Atoms don't form until about 1 million years after the Big Bang occurs. So for 1 million years after the Big Bang, it's still too hot for even an atom to form. After about 1 billion years, then we start getting to forming stars and stuff like that. Our solar system, our stuff we think forms, our galaxy formed around about 10 billion years ago. Okay? Did we get the time frame on this? I think I showed it to you before. When do we think this happened? About 14, 15 billion years ago. That's a big number. What?
Ours is 5.
Yeah, our sun is about 5 billion, our galaxy about 10 billion, kind of,
So we that little dot just explode. Nothing. So confused.
What was like the first thing you got?
What did you
Animals.
say?
Started with like
Well, no, I'm talking about. No.
Alright, so,
iron.
No question. Maybe a koala bear.
The koala was probably the first sign to tell us it wanted a koala.
Yeah.
All right. So, did it really happen?
Yes.
We think it did. But you can't just, well, I suppose you can just think it happened and not have anything to, back it up. But as scientists, we want to have as much evidence as possible. So, we got the redshift. The redshift suggesting that there is these galaxies that are moving away from one another. And if they're moving away from one another, that would suggest that at one point they were together.
Except for two, like galaxies are so far.
Or is that linked under red ship?
That's under H, right?
No, yeah, I know. But I mean,
That's number 1. Oh, yeah, that's number 2. Yeah, galaxies. And then we have this stuff that we refer to as cosmic microwave background radiation.
what does it say? What is it?
Cosmic microwave there.
So here's what cosmic microwave background radiation is. Back in the 50s, scientists start setting up things called radio telescopes. Visible light isn't the only energy that's being emitted by those stars. It also emits other kinds of radiation like X-rays and microwaves and gamma rays and all that good stuff. And we can't see those things, but we can pick them up, and we can interpret them through computers and stuff like that. So there's these guys, and they're trying to set up this telescope that's supposed to pick up microwaves, and they can never really get the scale to zero out. That they realize that there's always some kind of microwaves that are hitting their telescope. What they then go into is like, oh, it must just be left over from the Big Bang. There's just some energy out there that didn't cool down and form into a proton or a neutron or an electron or whatever. It's just kind of still out there. It's sort of, kind of like echoing after the Big Bang. And it's out there, and we can pick it up, and it doesn't really come from anywhere. It's not like coming from a star or from this galaxy or whatever. It's just sort of there. Okay? And that's one of the things that we use to sort of justify what's going to happen. Okay? Or what did happen, or what we think happened. Okay? All right. Now, let's confuse us even more. Okay? If the first question is, well, how did it all begin? The next logical question is, well, how's it going to end? Okay? And there's a couple of theories about it. But the one determining factor that we believe will most ultimately decide our fate is how much mass exists in the universe. A lot. And I bring your attention to this demonstration, which you can't see if you're watching the video, but I'm going to take the little yellow dimpled ball, right? And I'm going to throw it up in the air. So, throw it up in the air, right? And what happens? It comes back. Okay? I throw it up in the air, and what happens to it on the way up? It slows down because of what? Gravity. Gravity slows it down, eventually does what to it?
It stops.
Stops it, and then gravity pulls it back down to my hand. If gravity is the only thing acting on this ball, right, no friction, no air resistance, how much kinetic energy will it have when it gets back to my hands? Exactly the same. So how fast will it be going right when it gets back to my hands? Exactly the same. Gravity exists between any two masses out there in the universe. So there are these galaxies that are speeding away from each other, but what are they doing to each other? Gravitationally, they are attracting each other. If they're moving away from each other, but they're still gravitationally attracting each other, what will eventually happen to them? They'll stop. And then they'll come back together. And eventually, they end up where? Right back where they started. And we refer to that theory, okay, if the mass of the universe is large enough to produce enough gravity, eventually those galaxies will slow down, stop, and come back. And we refer to that idea in a fairly obvious way as the Big Crunch. These people that come up with these names are awesome. I tell you.
Crunch. Did you seriously
Do you like that?
crunch? Crunch?
So, here's it. Hold on to that thought just for a second. Okay?
No question.
So, the thing could be my hand throwing the ball representing the Big Bang. Right? All the energy at the beginning. Gravity slows it down, stops it, speeds it back up, and it ends up right back here. If all of the energy and mass in the universe end up right back in the same spot where it started, where it exploded 15 billion years ago, but obviously be longer then, what's probably going to happen again? It's probably going to explode
How do
again.
we know we aren't like the fifth time it's already exploded?
We don't, Sam.
Well,
That's so true.
That we may be, we may be the fourth or fifth time the ball has been thrown up in the air. Or we might be the 100,000th time the ball has been thrown into the air. But our perception of time began at the Big Bang.
How do we know that we didn't have time?
All of our measurement of time starts at 0 at the Big Bang. Could something have existed before us? Could have. Will we ever know about it? No. Because we can't look past 0 time.
But so that
It works.
But you didn't answer two of our questions. First of all, what is nothing? Like, what color is it?
So-
Is it clear? Or
Nothing!
but I know the same question, like, what is this happening?
Just a dot.
It was just a dot.
What's the background?
There was no background.
Cheetah print? I don't know.
There was no background.
What was it?
Nothing.
Like in space? Just a dot?
No. Space wasn't there.
Oh!
Space was in the
Background.
Space was in the dot.
Oh my god. Oh, he says it all.
I don't think
So, I just want you guys to know, alright? I'm, like, mocking you in this way, but, yeah, like, what was around it? Nothing. What do you mean nothing? Like,
No, but like also, like where did the dot come from?
the dot, well, if this is
Did it
true,
just like appear?
no,
God put
if,
it there to
if this is true, so if this was true, where did our dot come from? It came from the previous dot, right?
Where was the previous?
Yeah, when did it start? Who knows? Because we'll never know. We can never look past 0.
So if that means that our dot came from another dot,
Right.
that means that we're like not the first dot.
Exactly.
we're like
That means like we're like second.
So that means
There was another Alice somewhere.
Oh my god.
And you know what else? There was another Jude Law too. No.
You
There
guys
was never another Jude Law. There will never be another Jude Law.
No. You never will. What if you guys get married?
What?
Oh my god.
So, now, another option being that if there isn't enough mass in the universe, it'll just keep going. And we aren't toss number 5 of the ball, right? That
Number 1.
Yeah. Right. USA. Anyway, now, so hold on. I got a couple more things, and we can go questions. Okay. So, the question that comes out of this slide is what?
What will happen?
What's going to ultimately determine the fate of the universe? So the question is, come on, computer. So, how much mass is there?
A lot.
And the answer is, we don't know.
Oh, great. Wow, that's wow.
Well, it's like you should purchase an idea.
So, here. Why don't we know? Well, some things, well, it's not exactly their fault. It's not exactly their fault. So,
Wait, matter like, I mean,
So-
it's like here too.
some things, right? Some things give off light. So they're real easy to see, like stars. But some things, a lot of things, don't give off their own light.
I don't.
You don't give off your own light.
flashlight.
Is it on
But still, no, Amir, that's fine. No, Amir. So, okay, Amir. That's actually a good example. So, the flashlight. So let's say we're in this room and it's completely dark.
Yeah.
Okay. So the flashlight. Okay. We know the flashlight's there because it gives off its own light.
Yeah.
But the only other things we would know that were in this room would be what? What the flashlight shines on.
Oh, it can't shine on the whole thing.
Well, there's a lot of stuff out there. Right? And there are some things out there that maybe don't reflect the light of the flashlight. And if they don't reflect the light, would we ever know that they're there?
But Mr. Flint,
At least not that way.
they reflect a little bit of the light.
Some
reflected
things
off
don't.
How would they know, like,
Whatever the flashlight
what if, like, there's like another Earth in the galaxy?
That's the
Wait,
problem.
Mr.
We don't know.
Mr. Flashlight,
Because it
what do
doesn't
you-
give off its
What
own
do you
light.
mean it gives off, like, say something that
So-
gives off its own light?
For all
So,
we know,
if we use Miriam's example, okay? If we're in this room, right, and let's say it's completely dark, okay? We turn on the flashlight, right? You guys might all still be sitting there, but I wouldn't know you're there, okay? I turn on the flashlight. I can tell the flashlight's there. Why can I tell the flashlight's there? Because it's giving off light.
Well, you're holding it.
Okay, it's giving off light. Now, Allison, if I shine the light over here, I see Anthony, I see Pierce, I see Alex, I see Parker. Do I know any of you on the other side of the room are there? If you start screaming, well, now that's another way of telling if they're there. But if they give off some sign that they're there, but the desk can't start screaming.
Yes, it can. No, it can't.
I mean, the periodic table on the wall over there is not going to start screaming, right? Okay. So we refer to those things as dark matter,
The stuff that don't give off light.
stuff that doesn't give off light. Okay. Technically, yeah, because you don't give off your own light. Although, Pierce, you do actually give off like some heat energy. So I guess from that standpoint, you wouldn't necessarily be dark matter because if you could pick up heat energy, which we can, but a lot of things just don't, right? How do we know the moon's there?
It reflects the sun.
It reflects the sunlight. It doesn't give off its own light. If the sun isn't shining on the moon, do we see the moon? No. Right? Can you see the moon now?
Yeah.
Wait,
Can you see it now?
no.
We're inside.
Well, yeah, because there's no light coming off of it getting to your eyes, right?
You can sometimes see the moon.
Sometimes you can. But what I'm saying is, you can only see the moon if some of the light bouncing off of the moon gets to your eye. Right?
There's so much light out.
Right. I mean, and now it's on the other side. But hey, it's good.
Like, another reason why I can't see it is the sun's like giving us more light.
Well, right now it's on the other side, so we can't see it anyway because of the way we turn and stuff like that. But like during a lunar eclipse, you ever seen like a real lunar eclipse?
No.
It happens kind of not frequently, but But if the sun, right? If the Earth goes between the sun and the moon, now there's a shadow on the moon. Can you see the moon if there's a shadow on it? Why not?
It doesn't give off
Because there's no light bouncing off of it. That's dark matter. The moon is dark matter because it doesn't give off its own light.
Oh, it's own.
Its own, that's the key, right? We can see certain dark matter if light bounces off of it. But there's certain things that light might not bounce off of. A black hole. Light's not bouncing off of a black hole, right?
So that's why we can't see it, but we can tell something.
We can tell it's there, but remember, if we're going to try to determine the ultimate fate of the universe, what do we have to know about the black hole? How much mass it has. And if we know it's there, but we can't really tell anything about it, telling how much mass is there is kind of hard. Right? Here, go ahead.
Do you know how much mass I need to have?
We can calculate that, yeah.
Do we have enough yet?
We don't know.
But counting all, we can count matter.
That's true. Oh, no. With the amount of matter we can see, no.
Can we have clothes?
No.
Halfway?
I don't know exactly. But the idea being, though, so, Miriam, if you look, even in our solar system, there's a ton of things that don't give off their own light. But when we look like at a faraway star, we see the star, but we don't see its planets and stuff. I mean, other stars got to have planets like our star does, but we don't see those because they don't give off light. So it's hard to tell how much stuff is actually there. We could guess, but that doesn't do us a whole lot of good. We could guess, but... So, Chris, go ahead.
Well, are we allowed to start asking questions now?
Well, you've been asking questions anyway, so...
Well, we're done anyway.
yeah, I mean, this is the last slide, so...
Okay,
Go ahead.
you said it depends, like, on the amount of mass.
Right.
How it's going to depend, but, like, it's like, we all know, like, what is there in the beginning has to be, like, there in the end.
Right.
So then just,
But we don't know how much was there at the beginning.
What?
Yeah, what we're saying is, so Chris, not that I can do this, but there is a concept out there we refer to as escape speed. Based on the gravity of the Earth, I could, in theory, throw this ball upwards fast enough that it reaches the edge of Earth's gravity and it's still moving. And if that's the case, if Earth's gravity is no longer acting on it, but it's still moving, what is it going to do? It's going to keep going because of inertia. So that's the thing, is that if the explosion at the Big Bang, if the speed of those things at the beginning was fast enough that it effectively outruns the gravity of the universe itself, and it's kind of weird because it's the universe outrunning the gravity of the universe itself, whatever, but it'll just keep going. It won't stop and come back. So that's the idea of, we refer to that concept as escape speed. And if the velocity of all that stuff at the beginning of the Big Bang was greater than the escape speed of the universe, it won't come back. It'll just keep going. Okay, go ahead.
when, that Big Bang was just a dot, it had all that matter and everything, it should have, like, induced gravitational.
Except most of that matter wasn't in the form of matter at that point in time.
So it's
Through the whole idea of E equals mc squared, right? Mass and energy, right? Most of it was in the form of energy at that point in time. So it doesn't have gravity at that point in time. Because energy doesn't have gravity. Lauren, go ahead.
Okay, so I have a couple questions.
Good.
So the one is inside of like that one cone,
Yeah.
with like every single bit of matter that's in the universe right now in it.
Except it probably wasn't in the form of matter. It was probably in the form of energy. But yes.
So then the only way that so energy is converted into energy.
Yeah, like through the whole idea of E equals mc squared.
The more energy that we can bring is converted into matter.
Say again.
So the more energy that's converted into matter, the more likely we are to come back.
Technically, yeah, I would say so, because the more mass we have, then yeah.
And then is like that energy from the explosion, is that what's still like outward?
It's more probably the inertia from the explosion, right? This ball, as soon as it leaves my hand, gravity starts acting on it. But that doesn't mean it starts falling down immediately. It still goes up for a while because what was it doing when it left my hand? So inertia takes it, the upwards trip is a battle between inertia telling it to go forward and gravity telling it to go downward, right? And eventually gravity ends up winning and causes it to stop, but it doesn't win right away. So, regular podcast listeners, Grace just returned sans braces. For those of you that don't know Latin, sans means without. Alright, Kirsten, go ahead.
Okay, so what if every time it exploded, everything was opposite? What if every time it exploded, everything was opposite? And like, let's say last time was the first time it exploded,
Yeah.
then what we're like wearing right now is backwards.
Possibly, yeah.
That's weird.
Yeah, just because it explodes again doesn't mean that everything's going to happen exactly the same as it did the last time. Okay? Pierce, go ahead.
What makes it explode?
The fact that it has so much energy confined to a small space, right? It's a thermal expansion thing, right? All that stuff that's so hot doesn't want to be there, right? And that's generally probably what caused the explosion at that point.
So,
The fact that we're trying to get so much energy in one space just gets so hot, thermal expansion and all that kind of stuff.
So when it like it goes out and then it comes back in, does
Right.
it like explode again right away? Or does it
Probably,
wait a
yeah.
little bit, do
Probably the instant that it gets back to the point that it was the Big Bang, it would explode again. Just like, here's with this, right? How, we talked about what happens up at the top. Well, at the very top, actually, when it stopped. How long is it stopped for, though?
yeah.
Right? It's only stopped for that one instant in time, which is probably, if it explodes again and again, it's probably only that point for some instant of time. But that resets the clock when it explodes again. So we'll never know about it. Even though we're only separated by that instant in time, we'll never know anything that happened before us. We'll never know anything that happened after.
What if like you know how it explodes and comes back? You know how we look at that as being like a really long time? Like
Yeah.
Billions and billions of years.
Right.
What if that like to I don't know maybe something else seems like a split second of time which just keeps on.
What if it seems like this, right?
Yeah.
I mean, that's a possibility. You know, if there is something else that is observing our universe from the outside, you know, we don't have anything to suggest that be the case.
What if
But
we're like a small? What if we're like a
What
science
if-
reporter?
what if we are in a room and somebody's watching us in the room? What? Yeah, the Truman Show. Could be something like that.
So,
Yes.
Why do we cool off? Like, you know, you said like after like it cools or whatever.
Mhm.
Like, why does it?
Because it loses energy as it goes, right? Like Allison, when steam comes out of the tea kettle, right? It comes out as a gas, but eventually what happens to that steam?
It's like
It condenses back down to the water.
Yeah.
Right? So that's kind of
Okay.
right. Lauren, one more. We don't, but all of our evidence suggests that there was nothing. Because so Lauren, if you're drawing, like, if it was on a graph, right, and you draw backwards, they all peak at a certain point, and it just stops. Nothing else past that point. It's not like you go into negative numbers. It just, like, it stops.
So that's on Monday.
Test on Monday!
But you're
Yeah,
putting
questions? The objective sheet is up. I will modify.
Oh.